So in the Star Wars taxonomy of JVM language enthusiasts, our next speaker corresponds to the young Anakin Skywalker. His heart is in the right place, but he is constantly seduced by the dark side. I also believe that the inhuman amount of energy he displays when speaking is surely an indication that he has already begun the transformation to a cyborg. And if you thought the last talk was too dense for 9 o'clock in the morning, well, you ain't seen nothing yet. So here we have Daniel Spiewak to talk about functional data structures.
Wow. I am not sure I deserved any of that, Stuart. Okay, functional data structures in Scala. Now, the slide says in Scala, but the truth is that the majority of what I'm going to present here is generic, okay? I'm going to be talking about different functional data structures and kind of the concepts and ideas behind how they're implemented. And there will be Scala on the screen, but don't panic. It's not really that complicated, and the majority of this is just going to be conceptual and high level. So hopefully it's interesting, and if not, you can stone me later. If you don't know what a functional data structure is, you're probably in the wrong conference, but we're going to cover what they are anyway, just in case. But the main body of this talk is going to be the kind of the theory and implementation of 5 different functional data structures, loosely categorized as sequential and associative. Now, a sequential data structure is one that preserves insertion order and usually provides very fast access to either the head or the tail or maybe both, but not so fast access to the stuff that's in the middle. So random access, not so good. Associative data structures are kind of orthogonal to this. They don't preserve insertion order, so it doesn't even make sense to ask about a head or a tail. But what they provide is very consistent random access, very consistently timed access to anything in the data structure. And once we've looked at these implementations, we're going to take a brief moment to look at some of the aspects of modern computer architecture that affect how we have to design data structures in a way that the theory just does not reflect. Because there are some very surprising things that come from the fact that our code has to run on real machines, and we can't just do it all on a whiteboard. So what is a functional data structure? Well, a functional data structure, like almost everything in functional programming, is one that is immutable. Okay? It's an immutable data structure. Now, these are actually very easy to write. Okay? We could all write a functional array by just saying that every time you modify this array, you make a copy of it, and then you make the modification in the copy. Now, this is great because it satisfies the definition of immutability, but it is pathologically slow. It's just ridiculous if you do this. And it's not as good as we could do if we were doing it in a mutable sense. And this basically violates the first of our goals, which is comparable asymptotic performance with our mutable counterparts. Java util ArrayList has a constant time modification operation to any element in the array, and a constant time append. So we want to be able to achieve that in a functional setting. All right, obviously this is going to be really hard to do, but we want to try, right? And if we're just doing copy on write, that's not constant time, that's linear time. So this is not so good, and we want to do better than this. But if we're doing an immutable data structure where we're not getting linear time performance, then clearly we can't be touching every element in the data structure. Therefore, some of it must be shared between the old version and the new version. And this is what leads us to the idea of structural sharing, which we're going to be looking at a lot. This is the main tool. This is the main trick that we're going to use to try to make these data structures better than just linear time all over the place. So the first data structures we're going to look at are the sequential data structures, and specifically the singly linked list. Now, we're all familiar with this because it's really the canonical functional data structure, and Lisp is built on it, but we're going to look at it anyway because it teaches us some important lessons. So the complexity bounds for this data structure are somewhat unimpressive. We can get at the head of the data structure in constant time, But essentially, anything else we might want to do with it is going to be linear time, which is a little annoying, but in practice, you can make a lot of things work with it. The nice thing about it is it's very simple to implement. If you have a list, it is one of two things. It is either a cons cell with a head and a tail, or it is the empty list. And that's all you have to worry about. So now in functional languages, most functional languages anyway, when we want to implement a data structure, the way we do it is we look at the cases that represent this data structure, and then we implement those cases as an algebraic data type. And in Scala, algebraic data types are represented by sealed traits and case classes. So we've got our list trait here, and then it's got two cases underneath it, the cons case, represented by the double colon, since Scala likes ML, and nil. Okay? Cons and nil. Cons has the head and the tail, nil has nothing in it, and we can implement a cons method that takes an element and prepends it to the list, and it's very, very simple, and this is all there is to it. Okay, this is all there is to the list. So, as I said, the implementation is not interesting. We're not learning anything here. This is completely trivial. What we are learning is something about structural sharing. So let's say we had a list, foo, that had 4 elements in it, A, B, C, and D. We could represent it graphically like so. Now let's say we had another list, bar, that took H and prepended it to the tail of foo. If we represent this graphically, we could represent it by just another string of 4 nodes, sort of H, B, C, D, nil, sort of parallel to the one that we have for foo. But if we look at what this is in memory, it's a little bit different. H is prepended to the B, C, and D that are in foo, that are in foo. So B, C, and D in foo are shared between foo and bar. We could do this again with another data structure, baz. And we take M and N and prepend them to foo itself. And once again, the elements that haven't changed are shared between versions of the data structure. Now we could make copies of these, right? We could copy B, C, and D. We could copy A. That would be fine. It would be correct. But really, why bother? A, B, C, and D, they're all immutable. So one copy is just as good as another. We can share them, and we don't have to worry about different versions of the data structure stepping on each other. We could do this again with a 4th data structure, but I think you're kind of getting the idea here, right? We're sharing the pieces of the data structure that haven't changed between subsequent versions. Now, what we're seeing here is, especially with things like baz prepended to foo, where all of foo is being shared with subsequent versions, this is a very special property of the linked list. Okay? You cannot do another data structure that shares everything every single time with every version of the data structure. Other structures are going to have to copy some things. But our goal in every single case is to minimize the amount of copying and maximize the amount of sharing. And when we can do that, we can achieve very, very powerful abstractions, very, very powerful functional data structures that are still immutable and maintain these nice guarantees. So, Banker's Q. Okay? Well, what is Banker's Q? Well, Banker's Q comes from a motivation for a functional queue. We want a functional first in, first out data structure. And the most obvious thing to do here is to use the linked list, right? It's a nice sequential data structure, very easy to implement in a functional context. But it has a problem in that you insert at one end, okay? And you could insert 3 elements, A, B, C, and D, or A, B, and C. A, B, C, and D would be 4 elements, which would be confusing. And if you remove from the head, then you're going to get those 3 elements back, C, B, A. And that's not first in, first out. That is last in, first out. So it's not a queue, it's a stack. We want a queue. So we would have to insert at the head of our list and remove from the tail. But the problem is that inserting at the head is constant, removing at the tail is linear. And we could flip it around and insert at the tail and remove from the head, but again, one is going to be constant, the other is going to be linear time. And this violates our goal of comparable asymptotic performance because we have this nice queue data structure in mutable contexts that gives us constant time, insert, and remove. So Banker's Q is an attempt to do this. And its complexity bounds are very, very similar to the linked list, with the exception of the fact that we have access to the end of the structure. We have the access to the end of the queue in constant time, mostly. we're going to talk about what amortization means, but basically you should think of it as this last operation is not quite as constant time as the other ones. It's a little bit less genuine. So what is Banker's Q? Well, Banker's Q is a naive persistent Q. If you take the definition of functional persistence and the definition of a first-in, first-out data structure, mash them together in the dumbest way possible, you will get Banker's Q. It's really, really straightforward. You do it by taking two linked lists, two singly linked lists, one for the front, one for the rear. Okay? And for the front list, you're going to use that for dequeuing. You're going to remove elements from the front list, and you're going to insert elements into the rear list. Now, by itself, this is a really bad strategy, because the front list is just going to empty out, and the rear list is just going to fill up, and you're kind of in trouble. So what you do is every time the front list gets to be smaller than the rear list, you take the rear list, reverse it, and concatenate it onto the front list. Now, of course, this is a very expensive operation, but you're not doing it all that often. And this intuition is where we get to the argument about amortization. So whenever you want to claim amortization, you have to make the following argument. Most of the time, when you perform an operation, it is legitimately fast. Most of the time, when we dequeue, when we remove something from that front list, it is legitimately constant time. Removing the head of the list, that's constant time with no tricks at all. Some of the time, though, we have to do something that's a little bit more expensive. Some of the time, we have to do this whole reverse and concatenate jazz. And the argument we have to make is that the seldom run slow operation, okay, the reverse and concatenate thing, is exponentially infrequent with respect to the fast operation. And if you can make that argument, then you can take the slow operation, the cost of the slow operation, and sort of distribute it over the cost of the fast operation, and it all goes to a constant factor over time, right? Amortization. And the neat thing about laziness, if you do this with lazy singly linked lists, is it's literally taking this amortization idea, this distribution of the cost, and reifying it into the runtime. So this whole reverse and concatenate thing, if you have a lazy singly linked list, you can do that in constant time, because all you have to do is create a function that will do it for you. And you do have to pay the penalty eventually, but you pay it as you are removing from that front list. So you're distributing the cost over all of the operations, and you get a much more real-time guarantee that way. So what does this look like in code? Well, our data structure is going to have, as I promised, two lazy singly linked lists. In Scala, these are represented by stream. And we're going to separately maintain the size of these lists, so we can get at those sizes in constant time. And our NQ and DQ operations are just going to operate on these lists in exactly the natural way possible, take the result, and run it through a check function. And the check function takes a Banker's Q, and it looks at that Banker's Q, and it asks itself, is the front list still larger than the rear list? If so, then we're set, right? We don't have to do anything. However, if the front list has gotten to be smaller than the rear list, then we take the rear list, reverse it, and concatenate it onto the front list. Return the new Banker's Q, and we're set. So every time we perform an operation on Banker's Q, we return the new Banker's Q and run it through the check function, and that maintains our invariant. So with this, the NQ and DQ operations are very, very, very simple to implement. We just operate on the front list or the rear list, whatever operation we happen to be doing, and then run the result through the check function, and we're done. Very, 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 very straightforward, and surprisingly fast in practice. This is a very, very fast data structure when you actually run it. But it's a bit of a hack. Okay, we didn't really invent a new data structure here. We didn't do anything particularly clever. This is just a mashup of a data structure that we already had. It would be nice if there were a data structure that were designed from the ground up to be a good functional queue. And that data structure is the 2-3 finger tree. Now, the 2-3 finger tree is about as complicated as it looks, but it provides really, really nice complexity guarantees. Okay? Basically, we can get at either the head or the tail in constant time. We can append, we can prepend, first or last, and even things that we want to do in the middle of the data structure are probably going to be logarithmic time. So this is pretty awesome. In fact, the 2-3 finger tree is just about the ideal sequential data structure. It's pretty awesome. It is the ideal persistent DEC. It is the ideal persistent double-ended queue. Basically, if you take the definition of a double-ended queue and the definition of persistence, mash them together, and do the smartest, most complicated thing possible, you're going to get this. So how do we do this? Well, what is our motivation? Well, we want constant time access to both the head and the tail. So let's just take those elements, and we're going to pull them up to the root. Okay? We'll attach those elements to the root so that as long as we have the root of the tree, we can always get at those elements in constant time. And the rest of the tree is going to be, a subtree inside of that, right? We'll just descend recursively, and we're set. And this works great if all you're doing is reading, right? You're at the root. You can read the head or the tail in constant time. Super, super simple. The problem is if you are modifying this. So what happens if you want to remove the head? Well, we go down, we pull out the head, we remove that, that's constant time, but now we have this hole here, so we have to replace that element. So we walk down into the body, remove its head, pull it up, now we have to replace that one, so we're down and down and down, and before you know it, you're no longer constant time, you're linear time, because you have to descend halfway down the data structure. Half of the data structure has to be traversed. So we have to do something about this. And the trick we use is rather than just pulling up one element for the head and the tail, one element for the prefix and the suffix, we're going to pull up either 2 or 3 elements, and we'll give ourselves fudge factors to 4 and 1. We'll let it sort of slide around. But we're shooting for 2 or 3. And the argument kind of goes like this. If you want to remove the head, half of the time, you are going to have 3 elements at the head. So you remove one of them, now you're down to 2, but that's okay. I mean, 2 is all right. And so you're set. You just remove the head in constant time. Now the other half of the time, you're at 2, you remove one, now you have to find some replacements, so you walk down into the body, and you do the procedure again. But half of the time, you're going to be able to do that in the body in constant time. The other half of the time, you descend down. So half the time you're at the root, a quarter of the time you're in the body, an eighth of the time you're down further, and you see how this is going, right? The operation where you descend all the way down to the root of the tree is exponentially infrequent. So therefore, we have amortized constant time once again. Now graphically, this kind of looks like this. We start off with a single element, and then we're just going to keep prepending elements to this sequence. So we insert another element here, and that sort of splits the tree up into the prefix and the suffix. And if we keep inserting, we're allowed to keep doing that at the same level, right? These are constant time operations. But now we have 4 elements, and we have to do something here. So if we insert another element, what we have to do first is take 3 of these elements, package them up, push them into the body, and make room for the new element. And of course, this process continues, and so on, and so on, and so on. And you kind of get the idea, right? This is how it's going to go. So in terms of implementation, we're going to have 3 different cases to worry about for the tree itself. Okay? We have the singular finger tree, which we have to special case because it's really hard to take one value and split it up into a prefix and a suffix. And we have the empty finger tree, which we also special case. But the interesting case is the deep finger tree, where we have a prefix and a suffix and a body, which is another finger tree. And the prefix and the suffix are represented by digits, which is 1, 2, 3, or 4 values. And then the body kind of contains nodes, which are packages of 2 or 3 values. So these are just really, really simple containers here that 1, 2, 3, or 4 values, very easy to work with. So you see that if you have this, you have, say, 2, right? And you want to prepend an element to a 2 digit, you can do that in essentially constant time because all you have to do is create a 3 and just move the elements over. Very, very, very straightforward. And we can implement the prepend and append functions very simply, okay? Scala likes symbols, so we have plus colon and colon plus. Plus colon is prepend, so let's look at that, right? You take an element, and then you look at the prefix, and you see, do I already have 4 elements in my prefix? If so, then I need to take 3 of them, push them into the body, and the remaining 2 elements become the new prefix. Otherwise, we don't touch the body at all, and we just work with the prefix itself. We derive a new digit that's 1 larger in constant time. So this is a pretty awesome data structure. All right? It gets a little bit complicated, actually a lot complicated as we move further onto it, but it's the constraints that we get out of it are pretty neat. The problem is it is ridiculously slow. This is like a crazy, crazy, crazy slow data structure in practice. And we'll talk about why that is a little bit later. In the meantime, associative data structures. Or in this case, associative data structure, because I have less time. So the red-black tree, okay? This is really the canonical associative functional data structure, or at least it has been since Okazaki found a really nice way to encode it. So the complexity bounds here are pretty much what you would expect from a balanced binary search tree, right? Pretty much everything is log n. This comes from the binary nature of the tree and the fact that it's balanced. And there are a couple operations that are linear time. Nothing is constant time, but we're not really, really worried about that just yet. It's a bit annoying, but it's really hard to get constant time access over everything. That's just really tough. So how do we do this? Well, it's a balanced binary search tree. And we all remember our binary search trees where you have the element at the root is strictly greater than the elements in the left subtree and strictly less than the elements in the right subtree. So you have this very natural structure to it. But the problem with this is sort of the pathological cases where you're inserting in sorted order or maybe inverse sorted order, and you end up with kind of this linked list of nodes rather than a nice balanced tree. And the way you fix this problem is by rebalancing the tree, by fixing the tree just a little bit every time you modify it. Every time you insert a node, you're just going to fix up the tree just a tiny bit. And one way to do this is to take all of the nodes and color them, either red or black, and then follow two rules, two invariants that you have to preserve. Rule 1, every path from the root to the leaf to a leaf, okay, so every path down the tree is going to pass through the same number of black nodes. This is the guarantee that basically preserves balance. But, being the jerks that we are, we can play devil's advocate and say, well, we can satisfy this by just coloring the whole tree red. So the way you prevent this is you say that no red node can have a red parent. And if you hold to these two rules, you preserve these two rules at every step, you will have a balanced binary search tree modulo a logarithmic factor. Okay? It's essentially balanced. And so the trick is rebalancing after every single update. The trick is going to be this rebalance operation. So the structure of the red-black tree is not that interesting. I mean, we've all seen our binary search trees, and we just have a Boolean flag on there to determine what the color is going to be. We have nodes and leaves. I mean, this is all pretty much yawn. So the interesting thing is not the code that implements this, but actually the rebalance function, right? This is the hard part. And so it turns out that for this rebalance function, we are going to have to consider 4 different cases. Okay, 4 different cases that are all going to come back into sort of this central balanced red-black tree. So this is a balanced red-black tree centered on 3 nodes, x, y, and z. And then we've got A, B, C, and D. These are sort of subtrees that may be there, maybe not there. We don't care. We're not looking at them. So the first case that we have to worry about is the linked list case. Okay? We inserted in inverse sorted order, and we're sort of out of balance to the left. So what we do here is we grab the center node, we rotate around it, and we're back to center. The same thing happens if we are out of balance to the right. We grab the central node, rotate around it, and we're back to the middle. This is not all we have to worry about, though. Okay? We got one other case to concern ourselves with, and that is the zigzag case. All right, the zigzag case, we can't just grab the center node and pivot around it, because that would violate the ordering constraints of the binary search tree. So we go all the way down to the bottom, grab the third node here, pull it up, and then restructure around that. Of course, if you zigzag to the left, you also have to handle the case where you zigzag to the right. And the procedure is exactly the same. Grab the base node, pull it up, rebuild around it, and you're back to neutral. So if we can implement a function that handles this rebalance, then we can apply that function at every single node as we're rebuilding back up to the root. When we do an insert, we have to rebuild our ancestry. So we apply the rebalance function at every single locus back to the root, and we will have a balanced red-black tree. And that function looks like this. Can anyone read this? Wow. You have amazing eyes. You're not meant to be able to read this. It's kind of dull. This is basically just a bunch of really ugly pattern matching that implements what we saw in the previous slide. So if you understand the previous slide with all the sort of moving around and the different cases that we have to worry about, then you understand this function, even if this function is a little bit annoying to write. The point is, writing this is fairly trivial, and you can kind of get it out of the way in an afternoon, and you can use it to implement insert. So the insert function takes a key-value pair, and it does the standard binary search tree thing where you're checking if the key is greater than or less than and moving to the left or the right. And the only interesting thing is in the recursive case, as we're coming back up, we rebuild ourselves using this balance function. So the balance function takes care of ensuring that we are never going to build an unbalanced red-black tree. Pretty nifty. And again, this is a very fast data structure in practice. I mean, it's log n time, but the constant factors are pretty low. So a good data structure to hang on to. Now, we've seen sequential data structures, and we've seen associative data structures. I think it's time we look at a data structure that's kind of a combination of the two. This is a data structure that preserves insertion order and has very fast access to the head and the tail, but also provides extremely fast access to the stuff that's in the middle. And this data structure is the bitmapped vector trie, otherwise known in Clojure as vector. So this data structure was devised by Rich Hickey based on some work by Phil Bagwell. Both of them are here. So if you didn't already know what an incredible impact, obviously, Rich Hickey and Phil Bagwell have had on Clojure, go thank them after the talk because they're really incredible. So this data structure has some almost magical properties. Okay? The complexity bounds are just off the charts. We have append, we have first, we have last, we have nth, and update. I mean, all of these operations that we can do in constant time. And we've got a couple operations that are linear time, but we're not worried about those right now. All we're worried about are the constant time operations. All these incredibly cool constant time operations. Almost. All right, it's actually log base 32 event. Now, before you stone me for sort of lying on stage, let's think about what this means. Log base 32 event. Well, what is n? Okay, n is the length of the vector. Okay, it's the index of the vector, and the index is an integer. Now, integers on the JVM are bounded on the top by about 2.5 billion. So the highest number this could possibly be is log base 32 of 2.5 billion. Does anyone know what that is off the top of their head? It's a little more than 6. It's a little more than 6. So you round up and you get 7. 7. Now we're playing fast and loose with our big O notation here, but I think the point is that for any data set that actually fits in memory, log base 32 of n is pretty much the same as 1. So it's certainly close enough for me. And we're going to see in a bit that the constant factors here are so incredibly low that this data structure is, for all intents and purposes, constant time. So how do we do this? Well, we start with an array. And we're going to grow this array using copy on write semantics until we hit size 32. Now, remember I said that copy on write is bad, but everything is fast for small n, and we're really only going up to 32. So copy on write up to size 32, that's okay. When we hit our maximum size, we're going to take this array, and we're going to put it into an array of arrays. And then we're going to grow this array of arrays in kind of the same fashion by putting new arrays into it until that array of arrays hits size 32. Then we take the array of arrays and we put it into an array of arrays. Then an array of arrays. And the deepest level of nesting you can ever get is 7. So at most, getting to any element in the trie is going to require 7 array dereferences. Now, I don't care what platform you're running on. That is fast. That is incredibly fast. And graphically, it kind of looks like this. We start with our array. We grow it out until it hits our maximum size, which I'm pretending that 4 is equal to 32 because it fits better on the screen. And we take our array and we put it into the array of arrays, and then we continue growing on the side, right? We're growing this array out on the side, and as each array fills up, we put it into the array of arrays. And as soon as that array of arrays fills up, we push that into the array of arrays and continue the process. So this is how it's going to work. Now, how do we implement it? Okay? How do we go about this? Well, the way I chose to go about this is by handling each depth of nesting in a different case, okay? In actually a different type. I'm going to implement each one differently. And the interface that describes these different depths of nestings is case. And this basically describes operations where you're taking an index and finding the last array that actually contains that index, the endpoint array in the trie, or maybe updating a particular index in the trie. All of these operations are going to have different implementations in the 6 different levels of nesting that we need to concern ourselves with. And if we can implement each one of these levels of nesting, we will have our vector trie. Now, minor note of historical interest, Phil Bagwell in his talk on Thursday actually credited me with coming up with this. I did not. This was Rich's idea. I just beat him to the punch implementing it. Now, all of these different cases are pretty much exactly alike. So we're going to look at the one that fits on a slide. And that is the one case. Okay? This is our first level of nesting. And obviously, if we're looking up an index and when we're trying to find that endpoint array, every index is going to be in the same array because we only have one level of nesting. We can look at the updated method, right, where we're taking an index and a new value and we're trying to update that value in the trie. And this is where things kind of get a little bit interesting. So we take the array and we make a copy of it, right? Remember, copy on write. And then in the new array, we're going to update that particular index. And we find the index into the array by masking off the 5 least significant bits in the index we were given, and then using that to index into the array. Now, 5 least significant bits very conveniently corresponds to a range between 0 and 32. So this is really nice, right? This is why our arrays have to be a power of 2 in size. So anyway, you would imagine that for higher cases, right, for levels of nesting like 2, 3, or 4, you're just increasing the number of bit mask and array dereference operations that you have to perform, right? All you're doing is instead of just masking off the 5 least significant bits, for the next level up, you're going to be masking off the next 5 least significant bits. And then for the level above that, the next 5 least significant bits. So accessing, in total, right, accessing any element in the trie requires at most 7 array dereferences and 14 bit operations, okay? Bit shift and bit mask. And that's all we have to do. 14 bit operations and 7 array dereferences, and the performance is ridiculous. This is a crazy, 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 crazy fast data structure. For sort of normal-sized data sets, I'm talking about in like the tens or hundreds of millions in size, the performance factor is about 2 to 2.5 times the speed of Java util array list. Right? 2 to 2.5 times slower than Java util array list. Now, remember, 2 to 2.5 times is about 1 millisecond. So that's pretty ridiculous. This is a crazy fast data structure, and the reason it's so fast has to do with locality of reference. Now, locality of reference is an optimization that processors do and buses do and memory paging algorithms and optimizations do. Basically, everybody does this. And you're basically assuming that when you access a particular index into memory, a particular address, you don't want just that address. You probably want everything that's sort of around it. Because the chances are that in order to complete your task, right, in order for your algorithm to complete, you're not just going to need that one index, you're going to need the things that come after it. And you probably needed the things that came before it. So if you think about it, this is optimizing very specifically for loops and arrays. Now, this is precisely why the vector is so fast, because it really is just arrays. And so it works with locality of reference really nicely. And we've got these array sizes that fit just beautifully into modern cache lines. But for most of the things that we do in functional programming, we don't have arrays. And we certainly don't have loops. So what do we have? Well, we have pointers. We have objects. We have chunks of data that are sitting on the heap. And the heap is, in principle, randomized. So in theory, right, if we have, say, a linked list, we should have absolutely lousy locality with a linked list because just your pointers are sitting everywhere on the heap, and the GC is moving them around. And it's a mess. And it should be really, really slow. But in practice, it isn't. Because what is happening here is the JVM is doing something intensely clever. The JVM is looking at your object graph. And it sees, aha, we have an object of type cons. And this object of type cons has a pointer to an object of type cons, which has a pointer to an object of type cons. And, oh, I bet you're doing a linked list. I'm going to try to keep all of your objects kind of close together on the heap. And that way, you'll have a better chance of having locality, right? Getting a cache hit. And so if you let your JVM warm up and you have a program that's using a linked list, a large linked list, and then you take a core dump from that VM, and you look at the spot in memory, the spot in the heap that has that linked list, it's probably going to look a little bit more like an array than like a linked list because things are being kept together. So this is a very, very, very clever thing that the JVM does, and we should all be grateful for it because it's what makes the banker's queue really fast. It's what makes linked list very, very fast. It is also what makes the 2-3 finger tree not fast. Okay? Because what do we have with the 2-3 finger tree? Well, we don't have simple pointers from con cells to con cells to con cells. No. We have pointers to digits to nodes to digits to pointers to digits to trees to nodes to digits to nodes to trees to nodes. And the JVM sort of starts looking at this, right? It starts walking this graph, and it gets a couple steps in, and it just drops the whole thing on the floor. It's like, you're getting cute with your pointers. I have no way to help you. Your objects are going to live in totally random locations on the heap, so there. And the result is that your data structure has just awful, awful, awful performance. When you look something up in a 2-3 finger tree, odds are it's going to be a cache miss. And so you're going to have to go all the way to memory to get that data. And that is just insanely slow. So in practice, 2-3 finger trees tend not to be used that much, okay? Unless you have just insanely large amounts of data. And even then, they're just really, really, really bad data structures because of this locality property. And there are various tricks that you can perform, like Haskell actually has some hard-coded logic in its VM with respect to 2-3 finger trees, and there's some other things that you can do, but really at the end of the day, 2-3 finger trees are pointers to pointers to pointers to pointers to pointers to pointers to pointers in a very heterogeneous graph. And you can't really do a lot with that in the general case. So we're getting to the end of the material that I have, and I would be quite remiss if there was even the shadow of hint that I had come up with any of this. I didn't. People much smarter than I did. And these are some of the references, right? So if you're at all interested in functional data structures or really functional programming in general, look these things up, okay? Especially the top one, Purely Functional Data Structures by Okazaki. Read that book. Put it on your nightstand. Read it the first thing in the morning before you go to work. Sort of meditate on it during the day. It's an amazing book, right? It will really, really help you understand how to make your code fast in a functional context. All of the code for this talk is up, fully implemented in my GitHub account. This also has the data structure that I didn't present here, the fast mergeable integer trie by Okazaki and Gill. And yeah, thank you very much.